I should say first that the area bounded by some graphs, well, you can rearrange this one to be something like y is root 2 minus x all over root 2 minus 1, and then it's the equation of a straight line. And there is a method that you learn at some point in year 13 maths for how to find the area between two curves, y equals blah and y equals blur. There's some method for finding that area, but for this it would involve integrating horrible functions like this, which I really don't want to do. And in particular, it's not on the math syllabus. We don't expect you to be able to integrate an expression like this. So probably my first reaction when I saw this was, oh, I want an area, I should think integration, and then I saw this and I thought, I can't really integrate this. I mean, I probably can if I really try, but I don't want to integrate this. And probably people in chat were thinking, I don't know how to integrate this, which is fine. There's some sort of clever substitution you could do, but maybe you don't know about integration by substitution yet. I think it involves trigonometric functions, so maybe this is not the way to do the question. Okay, Naomi in chat has given us a different approach though, and that's to think about drawing a picture, which I suppose is a good idea in general, not just for this question, but for maths questions in general when you're thinking about an area, to try and draw a picture of what's going on in the problem. Okay, so here, I suppose, if nothing else, it will let us know where this area is that's bounded by these graphs. Okay, so y equals square root 2 minus x squared. That means x squared plus y squared is 2 if I do some rearranging, which is a semicircle. I mean, that's a circle, but this is a semicircle because it's just a positive square root. And it goes up to root 2, here and here. Circle centered on the origin with radius root 2. Okay, and this line is a straight line. Which points does this straight line go through? Well, when y equals 0, x equals root 2, so it goes through a point over here, and when x equals 0, y is do I want to do when x equals 0, or do I want to find another point that intersects this? There's going to be some line like this. Okay. And I suppose this area is the area we want to find between the semicircle and this straight line. Okay. So the suggestion is that we find, I suppose, this point and then use what we know about the area of a circle and the area of a triangle, I suppose, to work out what that shaded area is. Okay, seems a bit like I'm going to need to find the coordinates of this point over here. X is 1, y equals 1 is on both curves. So I've drawn this sort of completely wrong, haven't I? X is 1, y is 1, because 1 plus root 2 minus 1, yes, 1, 1. Okay, so I've drawn this kind of completely wrong because this point has coordinates 1, 1. Okay, I'm going to draw a new picture with this point over on the right hand side just to make people happier. So it's going to be here, that's going to be here, 1, 1. Brill. I want this area over here. Okay, smashing, and this is still not a very good graph, is it? Because this point over here has angle 45 degrees, because this line is y equals x up here. So now the question is, I want to find this area. I know the angle here, so everything's looking good. I want to find the area of this bit of the circle, and then subtract off, I suppose, the area of that triangle, which I'm going to try and do now. Let's go. So this bit of the circle is going to have area pi r squared, our radius is root 2, pi r squared times, and it's 45 degrees, which is 1/8 of a circle. That's the area between these 2 points around the outside, that wedge of the circle, slice of pizza shape. Interesting, that's pi over 4. But then I need to subtract the area of this triangle. The area of this triangle, well, it's got an angle of 45 degrees, and these two sides are length root 2, so I'm going to use half AB sine angle in between, half AB sine angle in between. I'm going to have to really concentrate here and remember that sine of 45 degrees is 1 over root 2. And I think that's going to give me pi over 4 minus 1 over square root 2 as my answer for what that area is. So I'm not going to write the factorisation down straight away. I think I want to talk about how you notice that. So one clue is that there are x and y terms over here. They've all got the same degree. They're all kind of cubic sort of terms. This is x cubed. This is x squared y. This is x y squared, and this is y cubed. I've seen those things before. I've seen x cubed, x squared y, x y squared, and y cubed from multiplying out stuff like x plus y to the power of 3. Okay, there's some numbers out the front here as well. But I've already sort of recognised these things over here. Okay, so then there's the question, it's not quite x plus y cubed, because x plus y cubed would be something more like, you know, x cubed plus x squared y, 3x squared y, plus 3xy squared plus y cubed, or something like that. The coefficients are a little bit different. I think I looked at this bit in particular and said, well, you know, if I was multiplying out something cubed, I'd expect the first term to be the first thing cubed, the last one perhaps to be the last thing cubed. This looks like the cube of 2y to me. So my next guess for what to try was, is this x plus 2y cubed on the left, secretly in disguise? You know, that's a hypothesis. I can see that the x cubed term and the 2y cubed term are going to match up. Do the middle two terms work out as well? And in fact, I'm going to skip doing the algebra on the screen, but in fact this thing on the left is exactly x plus 2y cubed. If you do the binomial expansion over there on the left, then this 6 and this 12 work out just fine, which is maybe a clue that we're onto something here. I haven't even read out the first sentence of this question yet, but we've factorised the left hand side. Okay, so that's 2 to the 30. We can take a cube root on each side and not have to worry about extra solutions because cube roots are unique for real numbers. This is 2 to the 10, which some people have told me is 1024, which I suppose is a relevant number for computer scientists, perhaps. Right, okay, that's a 0. 2 to the 10. Okay, we can do better than that. So the hard part of this question now is going to be engaging with what it actually wants us to calculate, which is the number of solutions to x plus 2i is 2 to the 10. Okay, so looking for solutions to this equation, and we're told that they're positive integers, which is important because if they're just any odd numbers, if y is pi, for example, then x could be 2 to the 10 minus 2 times pi. There's loads of solutions, but they have to be positive whole numbers. Okay, so someone in chat said it kind of feels like there's about half of the x's that you try work. That sometimes you put an x in, so you want x to be somewhere x is positive, and you want x to be somewhere it's going to have to be less than 2 to the 10. And it feels like, you know, you put a value of x in, you try 3, but then it turns out that 2 to the 10 is very even. Minus 3 divided by 2, you don't get a whole number out for y. So trying to guess these solutions like this feels like about half of them work. Here's the reason why. We need this thing 2y to be even. We want the sum of a positive integer and an even positive integer that's 2 to the 10. Okay, so I suppose importantly that's true, which means that this is true. Okay, so there are 2 to the 9 minus 1 possibilities for y. It feels like it might be 2 to the 9, but actually 2 to the 9 is not allowed, because if y is 2 to the 9, then x is 0, which is not positive. Okay, quick last check here. For each value of y, once I've plugged in my value of y, so long as it lies in this range, when I double it, I'll get something between 0 and 2 to the 10. I'll subtract that from 2 to the 10, and I'll get some value of x that will be a positive whole number. 2 to the 10 minus 2y is positive whole number for these y, for these values of y in that range. Okay, so each of these y values, there's a corresponding x value. Long story short, I think that means the answer is C, 2 to the 9 minus 1. Quick look at chat. Chat's actually got, for the first time on this live stream, a 100% success rate on this question. In radians, this equation, sine of t. Okay, so we've got to think about what on earth is sine of t doing in this range. So sine of t is a pretty strange function that we're trying to integrate here. Sine, I know, varies between 0 to 1 to 0 to minus 1 again. And sine of that is going to be, well, it's taking an input in radians between 1 and minus 1. And it's working out sine of that. Okay, so let's try and draw a graph of what this is. You see, I'm going to be thinking about this integral as the area between x is 0 and x, between t is 0 and t equals x. I want that area to be 0. Okay, so one strategy would be to integrate this function and set that equal to 0, but actually there's this incredibly difficult to integrate, and I think that's putting it lightly. So what we're going to do, well, I'm going to think about drawing this function. So sine of t looks like this. This is sine of t. Okay, so it goes up to 1, it goes down to minus 1. And then sine of that is going to look like, well, over here it's sine of 0. And then it goes up, because sine of bigger and bigger values is going to be bigger and bigger, until it gets up to sine of 1. Okay, so it's going up. I'm not quite sure how it goes up. It's going to go up to sine of 1. Okay, whatever sine of 1 is. After that, it's going to come back down again, because we're going to start working out sine of smaller numbers again. So it's going to come down again. I'm not quite sure how, but it's going to come back down to 0. And then sine goes negative, so this thing inside goes negative, and when sine goes negative, we're plugging in negative numbers into this outside sine function. I've realised I'm saying sine quite a lot and I need to point more at what I'm doing. So now it's going to have a negative answer, I think, because sine outside of a negative thing, inside sine, is going to be negative in sine. Oh dear. So because the sine of the inside sine is negative, the sine of the outside sine is negative too. That gives me a function that goes down until we get down here to sine of minus 1, and back up again until we finally get to a point where the sine of t is neither positive nor negative, because the sine of t is 0 again. And I've drawn something that looks a bit like sine of t, but crucially it's not sine of t. This is sine of t. And maybe I should draw more wobbly or something to show more. I don't really know what's going on here. Okay, but importantly, this is positive over here. It's negative over that bit. So I can't have x anywhere between 0 and, this is pi in radians, I suppose. I can't have x anywhere in between 0 and pi, because if I take x somewhere in there, then the integral will be positive. It won't be 0. I guess I could have x equal to 0. No, because they told me that x is bigger than 0. Okay, so I can't have x somewhere in here. If I put x somewhere in here, then my integral will be this area, and then subtract this area, because this is under the x-axis. So there's some negative contribution to the integral. But this part of the graph is, there's a sort of symmetry here. I suppose technically it's a glide symmetry, which is not one of the usual ones. So I'll explain a little bit that this part of the function looks like this part of the function, same shape. And to illustrate that point, I've drawn two different shapes. These parts of the function have the same shape. So the only way to get this area to be 0 overall is to take all of this bit, all of this second bit of area over here. I can't stop halfway through because then I'll have some positive contribution and a smaller negative contribution. So the only thing I can do, the only way to get 0 in total contribution, in total area contribution, I had to spell contribution, is to take x equal to 2 pi all the way over here. I'm going to move this all the way over here. Okay, once we move that over there, we get 0 now because we're integrating this positive bit of area and this negative bit of area. So overall, that'll be 0. So I think that's B, one solution. A and B are positive numbers, which is important because we're going to take logarithms of them. We're going to square them, we're going to multiply this one by 4 and get 1. Okay, the greatest possible value of A is... Okay, I have to admit, when I first looked at this, I started thinking about this as sort of the equation of an ellipse, but there's some logarithms in there, so I want to take my ellipse, and maybe this isn't a helpful way of thinking about the question, but I started thinking about this as like 4x squared plus y squared equals 1, which is an ellipse. I guess I got distracted by this 4, so this is an ellipse that goes through sort of 1/2, minus 1/2, y could be minus 1, y could be 1 up here. I think those are the points that it goes through, this ellipse. And then I was thinking about, I want to make a really big, so I want to make log base 10a really big. For me, that's my x. I want to make x really large. So if I want to make log 10a large, well, I suppose I make that really large by making x really big. So I want to make log 10b squared really small. That's a square, so it's bigger than or equal to 0. Let's make log 10b squared equal to 0, which we can do because we can set b to be equal to 1. If we make that 0, then I've got a nice equation to solve. It's going to turn out that I want log 10a to be 1/2, which is this point here on my ellipse. Maybe the ellipse was helpful after all. Not really sure. Here's my ellipse. I want this point over here. I want to make x really big. Okay, if log base 10 of a is 1/2, then logarithm rules. A is do each side to the power of 10, 10 to the 1/2, otherwise known as the square root of 10. So I think that makes it C. Maybe if I call this expression here, maybe if I give it a name, I can get into the question like that. So let's have a think about that. Yeah, so here's how I approach this question. I could give this a name. If I call this A or something, then the thing I want to calculate is A. Different dummy variable for the integral, but it's the same number. You integrate f between -1 and 1, and you get this number A. So I've got an equation now that says 6 plus f of x equals 2 times f of minus x plus 3a x squared. And now I'm a bit stuck because I've got some f's in here. I've got f of minus x as well. I've got 3a multiplied by x squared, which is a bit awkward to have around. What do I want? What do I want here? Well, I suppose I want just the integral of f between -1 and 1. So maybe this is a bit extreme, but something I could try is integrating each side from -1 to 1, which is a bit of a mad suggestion. It's going to have a pretty weird effect on some of these terms, but I'm interested in the way it turns this term into an a. I'm trying to turn everything into a's. Okay, let's try and do that. So if I integrate this from -1 to 1, with respect to x, that's going to be 2 times integral of f of, interesting, -1 dx plus 3a. A is just a constant, so I can bring it outside of this. It's a pretty complicated constant, but it's just a constant, so I can bring it outside of this integral. Okay, and now I've got some work to do. What is this? So if I integrate 6 between -1 and 1, I get 12, I think. If I integrate f of x between -1 and 1, well, that's what a is. So this left-hand side is 12 plus a. That's kind of why I did this. Over here, I've got, well, I'm going to come back to this one, but over here I've got 3a times this integral of x squared from -1 to 1 is 2/3. I think, yes, 2/3. Okay, last one here, I've got f of minus x dx. So this is what happens if you take the graph of f of x, so this is f of x or something, you look at this area, and then you flip f to be the other way around, flip f to be the other way around, so this is now over here somewhere, and work out this area. But this area is the same, area stays the same when you flip it left and right. So I think this is also 2a. I think possibly minus 2a, have a little panic. No, I'm going to stick with 2a, same area. If the area was underneath the parabola and we flip it around, you still get the area underneath the parabola. Okay, right, good. This is great news because now I've got an expression for a, 4a, 3a. I think I'm going to get the wrong answer here, aren't I? 4a, 3a, I get a equals 4. If I solve this equation, I get a. So this function, 4 minus 2 to the x squared, which is, oh my word, 4 minus 2 to the x squared is something like this. We're integrating it between a and 0. So we're interested in the contribution to this integral from, points between 0 and a. Okay, so if this direction is x, then I'm integrating 4 minus 2 to the x squared, some function like this, and when I'm working out the integral between 0 and a, that area there is I of a, at least to start off with. Okay, so as we increase a, to start off with, this thing we're integrating is positive, so as we increase a, the integral gets bigger and bigger and bigger. Later on though, once a is over here somewhere, where the function is negative, then I of a will be this positive bit of area minus this bit of area. So now the function is negative, and as we integrate, as we increase a, this integral is going to get smaller and smaller because we're adding on these kind of bits below the x-axis. Okay, so summary, we're integrating this function, and as we increase a, to start off with, the integral gets larger and larger, where we've got positive bits of function. But then later, once the function goes negative, we're now adding on negative contributions. So the integral is going down again. So over here, integral increases over here, whereas over here, integral decreases. And the turning point, or the change from increasing to decreasing, the point with di by dA equals 0, not increasing or decreasing as we change a, happens when we're here in the middle, with a point here where the value of the function is 0. Okay, said differently, what I want to work out is where is 4 to the 2 to the x squared equals to 0. So you could either think about this as being, well, this derivative is going to kill off this integration sign, or I suppose more carefully, I'm thinking carefully here about how the integral changes as I change a. Okay, this happens precisely when x squared equals 2, which is when x is plus or minus root 2, I suppose, but I want, what do I want? I want a positive number a. So I want to take a to be equal to the square root of 2 to be the value of this top limit of this integral. Because if I put that in, then I'll integrate just up to here. Before there, the integral was increasing. After there, it's going to start decreasing. That's why di by dA, the derivative of the integral, the area with respect to A is equal to 0 at that point.